Exponential growth and decay. When a quantity increases or decreases at a rate that is proportional to its amount, we get an exponential growth or decay. Examples of exponential growth are population growth and continuous compounded interest. Example of exponential decay is radioactive decay. The exponential growth and decay model. Assume that some quantity grows or decays proportionally to its amount. Let Q0 be Q sub 0 be the initial quantity and K the growth if K is more than 0 or the decay if K is less than 0 constant. Then, the quantity time T Qt is given by Q of T equals Q sub 0 e to the power of Kt. This is the quantity at time t. This is the initial quantity or the quantity at time t equals 0. This is the growth or the decay constant. When the quantity is population, we often write Pt instead of Qt, and then we get that P of t equals P sub 0 e to the Kt. This is the population at time t. This is the initial population or the population at time t equals 0. And this is the growth constant. Example: the amount of cells triples every 4 hours. How many cells are there after 7 hours? 2. When the number of cells will multiply by 5. It's best to do these kinds of problems using a chart. In the chart, we are going to put the times and the number of cells in few occasions. So again, we are reading the problem and we fill in the chart. It is given that the amount of cells triples every 4 hours. It means that when the time in hours is 4, the number of cells is 3p0, when p0 is the initial amount. Then, in 1, we ask how many cells are there after 7 hours. It means that I want to know what is the number of cells when the time is 7. We have to find it. And in 2, we are asked about the time at which the amount is 5 times p of 0. The first thing to do is to find the growth constant k. For this we are going to use that. It is given that P4, the number of cells after 4 hours, is 3 p sub 0. This is by the chart, but also I can use this because this is exponential behavior. So it is also p of 0 times e to the 4k. It's exactly the model when in the model I substituting 4 for the t. Now I'm looking at the 2 highlighted ones and I get that. I can cancel out p0. I get this. And now I can apply ln both sides. And I get that ln of 3 equals 4k, and k equals ln of 3 over 4. Now when I have my much improved k, I'm going to substitute this in my model, so I can improve the model. I don't want to use anymore that p of t equals p0 e to the kt, because now I have also the k. This is my improved model. Now we are ready to do more of the 1 and the 2. Let's solve first 1. 1 is the easy of the 2. We just have to substitute 7 in the model, and that's it. And we get that. This is more difficult, number 2. But again, we are repeating of what we did to find k, we are going to express this specific t in two ways. First of all, by the chart, it is 5p of 0. But also by the model, it is p0 times e to the power of t times ln of 3 over 4. This is from the chart and this is from the model. Again, I can cancel out the p0 and I get that. Now I can apply ln both sides and I get this. So I get actually that ln of 5 equals t times ln of 3 over 4. And I can solve for t. And I get that t is 4 times ln of 5 over ln of 3 hours. This is the exact solution. Please note that there is also a way to write it like this. Pt can be also written as p0 times e to the ln of 3 times t over 4. I can bunch up the e to the ln of 3, and e to the ln of 3 is 3. And I get this. Let's do another example. Half-life is the time it takes a radioactive material to decay to half of its original amount. We want to find k, the decay constant for the exponential decay model of a radioactive material with half-life of 150 years. Again, I will do a chart even though the chart is a little bit silly in this case, but it's better to get used to that. We know that after 150 years, because it's a half-life, we are getting to exactly half of the initial amount. Because half-life means that at that time, only half of the original Q0 left. So now again, I'm going to express the amount in 150 years in two ways. It's Q0 over 2 by the chart, but also I can use the model and I get that. So I get this and I can cancel out this to get that. Now I can apply ln both sides. And I get that ln of 1 over 2 equals 150k. And k equals ln of 1 over 2 over 150. I would like to note that ln of 1 over 2 is ln of 2 to the negative 1, which is negative 1 ln of 2, which is negative ln of 2. It's a negative number. It should be a negative number because this is radioactive decay, which means that the k is the decay constant and has to be negative. It is indeed negative. If you want, you can write it like this, replacing the ln of 1 over 2 by negative ln of 2. Example: express h, the half-life, as a function of k, the decay constant. Again, we are going to do a chart. What happened at h? The amount is half, so we get the amount of Q0 over 2. Again, we are going to express Q of h in two ways. One's using the chart, and one using the model, the exponential model. And we get that. We're going to cancel out Q0. We're going to apply ln both sides. Don't forget, we want to find h. The equation here is for h. So h is ln of 1 over 2 over k. And as you recall, as we did before, another way of writing this is negative ln of 2 over k. You ask yourself, how come we have negative here? Yes, we do. H is time. It has to be positive number. ln of 2 is positive, but don't forget that k is the decay constant and it's negative. So this is just fine.